Okay, hi everyone. My name is WiSwarm and I'm a final year PhD student in LIDS. Today I will talk about some recent work that we have been doing now for, well, a reasonable amount of time. We've been doing it now for almost 2 years. What we have been trying to do is build a new kind of system for doing multi-agent robotics applications based on some of the theory that we have been working on in our group, in Professor Modiana's group for the last 5, 6, even 7 years. So it's really a talk that is trying to take theoretical advancements that have been done in LIDS to real applied robotics problems and see if they work as we claim that we work in all of our papers. And hopefully the answer will be yes by the end of the talk. Okay. So first I will try to set up the theoretical foundations for the system that we are trying to build. And for that I will introduce this metric called age of information. And age of information is essentially just another network metric like throughput or delay, but it is slightly different from both of those. So think of a source that is trying to send packets through a network to a destination. This is fairly standard, but think of the source as trying to monitor some real-time phenomena. So say a sensor in a power grid or a control system that you're trying to control over a network. And so it is sending packets, and the thing that you're really interested in is not sending packets at a very high data rate or with very low latency, but what you're interested in is a closed loop with fresh information at the destination. Because if you don't have fresh information at the destination, then you can't really do monitoring or control. And your application is monitoring or control in these kinds of real-time settings. And so the way we define our age of information metric is simply we measure the amount of time that has passed since the destination last received a fresh update. So if the source generated a new update at time t1, and the destination received that update at time t1 prime, then the amount of freshness at the destination right now is just t1 prime minus t1, because it just received an update. Then for the next subsequent interval of time, during which it does not receive any update, this information just keeps getting older, so the age of information keeps increasing, because the information is getting scaler and scaler at the destination, until eventually a second update is delivered at time t2 prime, which was generated at time t2. So the age of information drops to t2 prime minus t2. And this gives us this familiar sawtooth waveform that you will see in basically every age of information paper in the introduction paragraph. And the goal of nearly all of age of information theory optimization papers is to keep this curve as low as possible. So designing network control policies, designing wireless scheduling policies, designing congestion control policies that will deliver fresh information from sources to the destinations. And the motivation for doing this is to do better monitoring and control. So in some ways what we hope is that age of information kind of acts as a proxy for monitoring or control cost. The better your freshness of information, the better monitoring and control you can do. And hence if you optimize for this metric, you'll get better monitoring and control instead of just optimizing for throughput or delay. And the way we do this is we consider this kind of abstract model. So this is the kind of abstract model that I have focused on in my research, especially when I came here in the beginning for the first 3 years. These were the kinds of abstract models that I was analyzing. So we have basically n independent sources, each of which is observing or controlling some phenomena in real time. And each of them is trying to send updates about this particular phenomena to a centralized base station. And the base station is basically trying to do whatever monitoring or control application that you're trying to run in real time. But the problem is that there's a single wireless channel connecting all of these n sources to the base station. So only one of them can talk to the base station in any given time slot. So what you need to do is design a scheduling policy that in some way prioritizes which source gets to talk to the base station in any given time slot. And the way we can formulate this is we can formulate the underlying monitoring or control task as optimizing some freshness metric, and the freshness metric, as I described, is the age of information. And we can put it in terms of a cost function. One particular example would be just a weighted sum of cost functions of all of these age of informations for all of these sources. And then we try to optimize the long-term time average of this kind of a cost function and find the best scheduling policy to do so under this kind of a wireless network setting. This is the most basic vanilla model in which you can analyze this kind of a problem. Then you can start adding bells and whistles. You can think of nonlinear age of information functions. You can start adding channel unreliabilities. You can think of packet drops. You can think of multi-hop networks. You can think of what happens when the weights or the functions of age of information are unknown. You can think of time-varying channel unreliabilities and so on. And over the past decade or so, there has basically been an explosion in the analysis of these kinds of abstract models and trying to solve all of these problems, some of which I have done as well. But what I won't discuss in this talk is how to solve these problems, because that is kind of old work in the sense that it is 3 or 4 years old. What I will show is that all of the theoretical analysis that has been done in trying to analyze this family of models can kind of boil down to this key idea, which is converting the problem into a restless multi-arm bandit and formulating and solving something called the Whittle index policy, which is known to be near optimal and low complexity. So it is a good solution to this kind of families of problems. And we can actually implement this and build a real system using this insight to gain significant performance improvement compared to traditional networking approaches for multi-agent robotics. So that will be the main focus of my talk. I will wait for questions at this point if you have questions regarding the theoretical part. But I didn't really do much theory, so hopefully there should be questions. Yeah. So what we want to do is go from theory and simulations to actual implementation. And as I said, there has been significant theoretical progress in Age of Information literature over the last decade. Age of Information was first proposed in 2012. Since then, there have been like 300 papers every year. That will boil down to like 3,000 papers in total. Yeah, so there has been a lot of work on it. And basically, every paper in Age of Information starts with the idea, oh, Age of Information works for IoT monitoring. Age of Information works for cyber-physical systems. Age of Information works for multi-agent robotics. But it is all written by theory people, like us, and people at LIDS. So we don't really know if it works, but we use it, yes, of course, to say that it works, and we believe that it works. And so the goal of this line of work that we started, which was WiSwarm, was to say, okay, all of our papers' introductions claim that it works. We should build a system to show that it works, and then demonstrate that you can gain significant performance advantages if you build a system with these principles. Okay. And to do this, we basically came up with a very simple application that really has freshness as the metric that you would want to optimize for. So we call this the mobility tracking problem. So think of mobile objects that are moving around on the ground, and each mobile object is assigned a UAV, and this UAV is supposed to track the motion of this mobile object. However, these UAVs don't really have any processing on board. All they have is some sensing and communication capabilities. So what they're doing is they have a camera that is downward facing, and it is trying to track the motion of this object, but it can't really do the image processing, so it collects video. It sends the video to a base station, which has powerful processing. The base station basically locates the target, sends back control commands to the UAV over Wi-Fi, and then this UAV basically tries to follow its target based on the received control commands. Now, in this kind of a setting, where you're trying to do high data rate communication with multiple robots over a single base station, what you're really caring about is information freshness. Because if the information at the base station regarding these UAVs and their video streams is not fresh, then the mobile object will move outside your field of view and you will lose tracking. If you lose tracking, then your application doesn't really work. So the thing that you want to optimize for in this kind of a setting is Age of Information. And yeah, so these were kind of the hardware pieces that went into our design. We basically built these drones, and what's the most important thing that you should notice here is that on top of each drone is essentially a Raspberry Pi Zero. A Raspberry Pi Zero, if you know about microcontrollers, it can't do anything. It basically has like 512 megabits of RAM. So it can't do anything, but it can connect to sensing interface. It has sensor interfaces, so we had an HD camera connected to it, and we had a high-power Wi-Fi antenna connected to it. So it can collect video, and it can send this video over Wi-Fi to a powerful compute node, and then receive back control commands and run the microcontroller of this UAV to tell the UAV where to follow these cars. And we use basically things like these QR codes, we call them AR tags, to figure out how to locate these cars in this room environment. At a high level, what our system does is it does 3 key things which come from Age of Information literature of the past decade. So the first thing that we do is at the source. And the sources being the UAVs, so we call them followers. So think of all of the networking stack in almost all modern networking implementations. They typically only implement FIFO queues, so first in, first out queues. All packets that come in must get delivered, and they must be served in this first come, first served order. In freshness of information applications, what you want is that if there's a new packet being generated at the source, and you have old packets in the queue, you should replace all of the old packets with the new packet and then let the new packet start processing. Because all of that old information becomes irrelevant as soon as this piece of new information was generated. So what you want really is last in, first out queues instead of first in, first out queues. But the problem with most of the networking stack is that you can't really go into the MAC layer or even the lower layers of the OS to implement last in, first out queues, especially in something like a Raspberry Pi Zero. So what we did was we implemented last in, first out queues at the application layer. So every time a new video frame was generated and the Raspberry Pi got a new video frame from the camera, we had a one packet buffer or one video frame buffer internally at the application layer, and we would replace these video frames as soon as they were generated. So we were never sending a video frame that was old. Every time a fresh video frame was generated, we replaced all the video frames that were never even sent, because they aren't really useful for this particular tracking application. So that was kind of one key idea, and this boils down to a long line of queuing theory literature in Age of Information, which showed that last come first served queues are indeed optimal if all you care about is information functions. So that was the first thing. Then the second thing. The second thing is basically implementing the Whittle index scheduler that I was talking about in the earlier slides. So if you have these end sources and there's a base station that is trying to talk to all of them, then what you want to do is run a centralized scheduling policy that knows exactly how to prioritize each of the information updates from each of these sources so as to optimally control the flow of information in this network. And the way we run this is by formulating the problem as a restless multi-unbounded problem and finding something called the Whittle index policy, the details of which I'm happy to talk about offline, but I won't really discuss in the talk today. And this is basically one of the major theoretical contributions of my PhD thesis, but what we did was we implemented this again at the application layer, but at the base station. And what we did was we implemented this over Wi-Fi. So if you know about Wi-Fi, the way it works is if n nodes are trying to talk to a base station, which is a Wi-Fi router, then Wi-Fi doesn't really implement a centralized scheduling policy. What it does is it implements something like a distributed scheduling policy where two nodes will try to talk at the same time. If they sense that another node is trying to talk, both of them will start a random counter, and then whosoever's counter runs out first, that node gets to talk. And this leads to kind of a distributed back-off mechanism-based medium access scheme. This inherently has a lot of overhead because of this distributed nature and because different nodes don't know information about the other nodes' information needs. So what we do instead is, because the base station knows everything about the network, it knows how long it has been since each UAV talked to the base station and how long it has been since each UAV tracked the particular object in its field of view. It can perfectly calculate which UAV needs to talk to the base station most urgently, and this is what this scheduler essentially does. And it can then send a polling command to that particular UAV to respond with a video frame. And this basically kind of sidesteps the entire issue of distributed scheduling by implementing a layer of centralized scheduling over Wi-Fi's distributed scheduling. And so at the application layer, what we're doing is implementing this polling plus control mechanism, which kind of eliminates all of the overhead that Wi-Fi's inherent distributed scheduling mechanism inherits. And the third thing that we did was think about all of the time-varying aspects of this application. So what if there are two drones, and one of them is tracking an object that is mostly stationary, and one of them is tracking an object that is moving very fast? You probably want to give much higher scheduling priority to the drone that is tracking the object with high speed rather than the object with low speed. But objects can change their speeds, and they can probably even change their speeds adversarially. So again, one of the theory papers that I wrote earlier in my PhD was about incorporating online learning into this wireless scheduling framework to provably show that you can learn these scheduling policies in an online manner, and you can derive some nice regret plans. And in this project, what we did was we incorporated this layer of online learning, which can again be done in a computationally efficient manner, so you can do it in real time, into this centralized scheduler. And we were able to incorporate it and show that, oh, this system actually works in practice as well. Okay, so there were three key things that we did. It was queuing at the sources, centralized scheduling via polling, and then incorporating online learning in the centralized scheduling. Okay. And once we have all of these pieces together, hopefully the videos should show you that we gain significant performance improvements. So this is probably the most interesting part of the talk. So you will see 5 drones trying to track 5 cars in real time. and this is our system. Now you will see Wi-Fi. You will see age of information plotted here, error plotted here, and tracking plotted here. You'll see Wi-Fi works very poorly even with 2 drones. And it kind of works, but not really, and the age of information is pretty high. It's like 0.2 to 0.4 seconds. And now we will show the same thing for 2 drones with our system, which we call WiSwarm. You'll see much lower AOI, so this is around 0.1 seconds or even lower, and much lower tracking error, almost 5 times lower tracking error. And you can see this in the 2D plot as well, where we are able to deliver almost perfect tracking with our system. And this is just for 2 drones. Now we can do the same thing for 5 drones as well. Wi-Fi doesn't work for more than 2 drones for our particular system and the settings that we have. So we can basically get far better scaling than standard networking algorithms. And all of this is done at the application layer. So we are taking off-the-shelf Raspberry Pis and a UAV and just writing code in Python. We are not going into the Mac layer or building our own Wi-Fi chips. And we are still able to gain significant performance improvements. Yep. So these are some numbers. I won't really go over the numbers in detail. I think the video covers all of it pretty well. But yeah, so one of the key insights is that we did all of it at the application layer without changing any of the Mac layer or the physical layer. But what we believe is that if you go and build your own Wi-Fi chips and implement this new protocol as 802.12 instead of 802.11, we think that this can deliver even larger performance gains because you don't have any of the signaling overheads across the layers that we had to incur because we implemented everything at the application layer. So yeah, so the key takeaways from this talk are that if you have a multi-agent robotics application that needs highly iterative communication with multiple robots, and if you're trying to do computational offloading, so you're moving computation from the robots back to the cloud or to a base station or to an edge compute node, and you want to do coordination across a large group of robots over wireless channels, then you should probably use our system instead of Wi-Fi. Or if you are trying to use 4G or 5G, then you should call up your 4G or 5G provider to ask them to incorporate an age of information scheduler in the base station, which is something that I'm trying to talk to people at Nokia Bell Labs about. But yeah, let's see that later. And that's it. Yep, I'm happy to take questions.
So, any questions?
Yeah.
Thank you for the talk. So you talked about the scheduling for sending the sensing data from the UAVs to the base station. The
Yes.
question is, do you also consider the scheduling for sending the control signal? From
No. So yeah. Every time we send a polling command, we append the control information with the polling command, and that control information is broadcasted to every UAV. So we just keep broadcasting the control information frequently so that everyone knows the control. So this kind of allows for some kind of redundancy in the control information so that the UAVs never lose control. This is kind of specific to our application, yeah.
Maybe this is a naive question.
Sure.
Like, can it happen that the sense data, the ordering, time ordering can change? Or is it like we assume you receive the data with the order they're sent?
Oh, so you're saying that sometimes you send older data after you send newer data?
You
So
receive older data after you
Yes.
receive.
So I think we try to eliminate this using this kind of LIFO queue here. So what the LIFO queue does, let's see. What the LIFO queue at the sources does is basically every time a newer packet is generated, a newer video frame is generated, if the Raspberry Pi Wi-Fi chip was trying to transmit an older video frame, it will just replace the entire buffer with a new video frame. So you never want to transmit an older video frame. It's just a waste of resources. Every time a new video frame is generated, you just replace everything that is in the queue and try to transmit the newer one. So you never try to transmit anything older. So it shouldn't happen that you get out of order updates, but there is work in theory. People have tried to analyze what happens if you don't have this kind of perfect control of queuing at the sources. What happens if you are sending packets to an arbitrary network and you get out of order updates? How should you figure out how to combine them to get best information functions? There are people who have considered that in theory. Yes.
Sure. Any other question?
Yeah.
So you consider time division manners, right?
Sorry.
Time division and scheduling between the
Yes.
database. So
Exactly.
if we consider frequency division manners,
Yeah.
do we still need to consider age of information?
Yeah. So in this kind of an approach, what we had was the interference constraint was that only one source can talk at a time, right? So if you have a frequency division multiplexing system, so something like a non-orthogonal multiple access system where multiple sources can talk at a time, you will still have some constraint. So you will have some constraint as saying, say, 10 sources can talk to the base station at one time. But what if now you have 100 sources? So you will still need to do some kind of scheduling, right? At some point, at some system scale, you will run out of resources, whatever wireless resources you have, and then you'll have to do scheduling. It's just that the system scale might be different. For us, it was just one, so the system scale was evident at the problem of even 2 drones and 5 drones. But with non-orthogonal access, you might be able to do it you might be able to get away with doing experiments with 10 drones, but you'll have problems with 100 drones. But at some point, you'll start having problems.
Thank you.
Okay, thanks, Vishen.
Thanks.
Nice talk.